All right, this is gonna be 9.4. Uh, we briefly went over this in 9.2, right? So it's important that you guys kind of did lesson 9.2. Not all too important, but we kind of talked about the fact that the double slit experiment proved that objects on an extremely small scale acted like a wave as well as a particle. And that was especially true for things like the electron, right? If you get things onto the really small scale, they start acting like a wave. Well, how is that proven? Right? It was proven because the wave, as you threw electrons through either of these two slits here, well, they made something called an interference pattern. They made like a wave pattern, a diffraction pattern, right? Diffraction pattern is something you only see occurring on waves, but you saw it happening to things like electrons, particles, and it made an interference pattern on the back. So this is something that you actually have to remember, that the double slit experiment proved that not only light was a wave, that electrons and other particles also were waves as well. So light is an electromagnetic wave, something we call an electromagnetic wave. And electromagnetic waves do not need a medium to travel through, which means they can travel through the vacuum, right? Like space. So light doesn't actually need anything. Whereas sound waves and others are called mechanical waves, right? Sound waves need air to travel through, right? If you didn't have air or any particular gas medium, you wouldn't have sound. And so that is the difference between something called electromagnetic waves and something called mechanical waves. And electromagnetic waves consist of two oscillating electric and magnetic fields that act in 90 degrees to one another. You just need to know that there's a magnetic and electric field here. You don't need to know how it works, but you just need to know that it's there. Something else you do need to know is that we can artificially generate electromagnetic waves. How do you think we have radio waves, right? How do you think we have internet? How do you think we have Wi-Fi? Well, we can generate electromagnetic waves. We can artificially create electromagnetic waves by moving an electron up and down, right? And there, so by moving an electron down and up, we send a wave, we cause an electromagnetic wave, and this electromagnetic wave causes an electron, the receiving tower antenna, to also oscillate. And that's how we send information, right? That's how we send information. So light is an electromagnetic wave. And that's pretty much the only thing you actually need pertaining to this. So light is also something called light is not only a wave. Light also not travels as a wave. Well, we can consider light behaving as a particle as well. And particles of light are called photons. What's the significance of this, right? Well, let's go back to the atom. Let's go back to the atom. So let's say we have a hydrogen atom. Let's say we have a hydrogen atom here. And when electrons go up an energy level, and I'm assuming that you guys have some idea of energy levels in the first place from chemistry. So let's say electron goes from energy level 2 to energy level 3, right? It goes up a level. Hold on, let me clip something. So it goes from energy level 2 to energy level 3, right? Well, it needs energy first off. For an electron to go up a level, it needs energy. Well, where does it get that energy? It gets that energy in the form of light, right? Or electricity. It really depends. But here we're going to be mainly talking about light, an energy of a photon. So an energy of a photon is absorbed by the electron, and so the electron now gains energy and moves up a level. Well, what happens when the electron eventually goes down a level? Well, when the electron goes down a level from level 3 to level 2, it emits the same exact amount of energy in the form of light. And that energy, let's say we have red light that comes in. Red light comes in, electron absorbs that light, electron goes up a level, then electron goes down. Well, the electron will emit that same red light back, as you can see in the GIF. Right? In the GIF, you see that the electron is absorbing that red light, goes up a level, and when the electron goes down, you'll see that the electron emits red light as well. Which is how in the real world you have light at all. How you have neon lights. Right? Neon lights work by the same exact principle. You excite the electrons go up levels, and when the electrons go down levels, they emit light, which is what you guys see. So, energy, light has energy. We can calculate the energy depending on its frequency, right? So the frequency of light determines its energy. And on your reference table, you'll see on the second page that this is the electromagnetic spectrum. And you'll see that as you go to the left, you have a higher frequency, which means you have the most energy, right? And as you go to the left on the wavelength side, well, your wavelength decreases, which makes sense because if you have a higher frequency, you have a lower wavelength. So gamma rays we classify gamma rays as having a frequency between 10 to the 19 and 10 to the 21. Right, and so humans are only adapted to see visible light of certain frequencies from 3.84 to 7.69. So we can only see in this frequency range. We can't see anything else. We can't see radio waves. We can't see long radio waves. We can't see AM waves. We can't see FM waves. We can't see microwaves. We can't see infrared. But what we can see is visible light, all the colors of the rainbow. And the formula used to calculate the energy of a photon with a frequency is this formula right here. The energy of a photon is equal to HF is equal to HC over wavelength. Well, what is H? H is Planck's constant on the first page of your reference table, right? So right here, Planck's constant is equal to 6.63 times 10 to the negative 34 joules per times second. So let's solve this question. So you have an argon ion laser, wavelength of 488 nanometers, which means that this, if you convert nanos to meters, nano is 1 nano is 10 to the negative 9. So this must be 488 times 10 to the negative 9 meters. And if you simplify it, move the decimal place over 2 times, right? So 2 spaces, so it's negative 7 meters. And you want to know what was the energy of this photon? You know Planck's constant, which is negative 34 joules times second, and you know your speed of light. So you instead of using HF here, you are going to use HC divided by lambda. And then you're going to solve for energy. I'm not going to do it for you. Make sure you use parentheses, all right? All right. So let's measure the energy that is moved between levels. So here you have your hydrogen atom with all the added levels labeled. Well, how do we So let's look at level 2. At level 2, you have negative 3.440 electron volts. So these are your energy levels, right? So on your hydrogen atom, you have energy. This is negative 3.40 electron volts. At energy level 3, you have an energy of negative 1.51 electron volts. So how do we calculate the energy difference? Well, we just subtract them. We just subtract them to those two. So let's do a practice problem. So you have a photon. It goes from n is equal to 5. Goes to n is equal to 5, right? So electron drops from n is equal to 5 to n is equal to 3. So your initial energy negative 0.54 electron volts. Your final energy is negative 1.51 electron volts. And on the reference table and the formula indicated in the previous slide, the energy of a photon is equal to EI minus EF. So this minus this gives you 0.97 electron volts. So this is the energy of the photon that's emitted when the electron goes from level 5 to level 3. So that's the energy in electron volts. 5b is the same thing. 5d is actually the same thing as well. And so 5c, we're going to do 5c. Actually, 5d is not the same thing. We're going to do 5c first. So 5c says an electron in the C level of mercury returns to the ground state being A. Which photon of energy could not be emitted by the atom during this process? Now, when an electron falls down levels, it doesn't necessarily have to go from C directly to A. It can take a detour, right? It can first go from C to B, emit the energy difference between C and B. So the energy difference between these two levels, which is 0.22 electron volts, it can also, and then once it's at B, it can then go from B to A, and the energy difference between B and A is 4.64 electron volts. So in the process of going from C to A, in this situation, I emitted 2 photons of 2 different energies. If I'm going directly from C to A and I calculate the difference, I emit an energy difference of 4.86 electron volts. And that's one possible photon value. So A, B, and C are all possible, and D is the only impossible energy that could be emitted when an electron goes from level C to level A. D, I'm gonna just explain D real quick. I'm not gonna do the math. So a photon is emitted when an electron in a hydrogen atom drops from N2 to N1. So it goes from N2 to N1. And they want to know, well, what type of photon is emitted? Well, first you have to calculate the difference here, and the difference is going to be, so the energy of this photon is going to be 10.2 electron volts. Well, we need to know what type of photon, right? We need to know what type of light this is. Well, we have to first convert this to joules. And on the first page of your reference table, you will see that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So you have to first convert this and then you'll get some sort of value. I'll actually do it, I guess. 10.2 times 1.6. So you're gonna get so this energy of photon is equal to 1.632 times 10 to the negative 18 joules. And now that you have the energy in joules, what you're gonna do is you're gonna convert this, you're gonna figure out what your frequency is. You know what your Planck's constant is. It's 6.63 times 10 to the negative 34 joules times second, which you can look on your reference table. And then you solve for frequency. And if I recall correctly, you get divided by 6.63. You get, well, let's look at our reference table. You get 2.46. So your frequency is 2.46 times 10 to the negative 14. Negative 14 hertz. So if you go to your reference table, right, we have a frequency of 2.46 times 10 to the negative 14 hertz. I didn't use a calculator, so I might be wrong on the frequency, but what I'm about to say still works even if I'm wrong. Rather, the logic still stays the same. So I have a frequency of light is 2.46 times 10 to the negative 14 hertz. And if you look at your reference table here, yeah, you're going to look for that same exact frequency. Again, you're looking for 2.46 times 10 to the 14. 10 to the 14 is over here. 2.46 is less than 3.84. But what still falls under 10 to the 14th is infrared. So we have infrared light here. Actually, let me just solve this real quick. Actually, no, I'm not going to solve this. But that's the end of this video. All right. If you have any more questions about this, just ask me in class or ask me for help.